Characterization and modeling. Characterization and modeling are pivotal to the development and advancement of fuel cell technology. By assimilating theory and experiment, careful characterization and modeling studies allow us to better understand how fuel cell works, often paving the way towards further improvements. Because these subjects provide great insight, each has been given in the lectures. We will dedicate full lectures to these fuel cell modeling and fuel cell characterization techniques. These lectures will lead a practical understanding of how fuel cells are tested, how to diagnose their performance, how to develop simple mathematical models to predict fuel cell behavior. What is fuel cell technology? So, the initial lectures are devoted to understanding the fundamental principles of the underlying fuel cells. However, no treatment of fuel cell is complete without a discussion of the practical aspects of the fuel cell technology. So, in the later part of the lectures, we will study and we will introduce a major considerations for fuel cell stacking and system design, as well as specific technological aspects related to each of the five major fuel cell types. Then you will gain an insight into state of art in fuel cell materials and fuel cell design, as well as historical perspective on the development of practical fuel cell technology. Fuel cells and the environment. If employed correctly, fuel cells are environment friendly. In fact, this may be their single greatest advantage over the energy conversion technologies. However, environmental impact of fuel cell depends strongly on the context of their use. If they're not deployed wisely, fuel cell may be no better than a current fossil fuel conversion systems. So, in the end lectures, we will be able to evaluate possible fuel cell deployment scenarios using a technique known as a process chain analysis, and we'll be able to identify promising fuel cell futures. One such future referred to as the hydrogen economy is illustrated in figure 1.13. In this figure, hydrogen fuel cells are coupled with electrolyzers and renewable energy conversion technologies such as wind and solar power to provide a completely closed loop, pollution free energy economy. In such a system, fuel cells will play a prominent role, with a primary benefit of being their dispatchability. When the sun is shining or the wind is blowing, the electricity produced from solar and wind energy can be used to power cities directly, while producing extra hydrogen on the side via electrolysis. Anytime the wind stops or night falls, however, the fuel cells can be dispatched to provide a demand power by converting the stored hydrogen to electricity. In such a system, fossil fuels are completely eliminated. Currently, it is unclear when, if we ever, the hydrogen economy will become a reality. Various studies have examined the technical and the economic hurdles that stand in the way of the hydrogen economy. While many of these studies differ on the details, it is clear that the transition of a hydrogen economy would be difficult, costly, and lengthy, and it does not count on the anytime on it happening anytime soon. In the meantime, we have fossil fuel world. Even in a fossil fuel world, however, it is important to realize that fuel cells can provide the increased efficiency, greater scaling, flexibility, reduced emissions, and other advantages compared to conventional power technologies. Fuel cells have found and will work to find niche applications. These applications should continue to drive forward progress for decades and come with or without the hydrogen economy dream. So what all have we studied in these lectures? So we have basically studied the fuel cell is a direct electrochemical conversion device which converts electricity from one form, that is a chemical energy, to electrical energy through electrochemistry. Unlike a battery, fuel cell cannot be depleted. It is a factory which will continue to generate electricity as long as the fuel is supplied. At a minimum, a fuel cell must contain two electrodes, a anode and a cathode, separated by an electrolyte. Fuel cell power is determined by the fuel cell size. Fuel cell capacitor energy capacity is determined by the fuel reservoir size. There are five major types of fuel cells determined by the electrolyte. Electrochemical systems must contain two coupled half cell reactions, an oxidation reaction and a reduction reaction. An oxidation reaction liberates electrons. A reduction reaction consumes electrons. Oxidation reactions, it occurs at the anode electrode. Reduction reactions, it occurs at the cathode electrode. Four major steps in generation: electricity, reactant transfer, electrochemical reaction, ionic and electronic conduction, and product removal. Fuel cell performance can be assessed expressed by a current voltage curves. Current voltage curves show the voltage output of a fuel cell for a given load. Ideal fuel cell performance, it is dictated by thermodynamics, and real fuel cell performance is always less than the ideal fuel cell performance due to losses, activation loss, ohmic loss, and your concentration losses. So this was your brief introduction to fuel cells. Brief but quite long introduction. Now we will study in detail the fuel cells in the subsequent lectures.